The broadcast is now starting. All attendees are in listen-only mode.
Good morning, everyone. This is Julie McDonald with Microcom Technologies, and I'd like to thank all of you for attending today's webinar with MetaGeek. Today's host is Joel Crane, a technical trainer there at MetaGeek, and he'll be presenting today. If anyone has any questions, please feel free to submit them in the question box, and I will ask them to Joel, and he will answer them at the end of the presentation today. Joel, I'm finished for now, and if you're ready to go, it's all yours.
Great, thanks, Julie. Welcome to Design Considerations for Dual Band Wi-Fi. In this webinar, we're going to go over some of the basics of how some things to keep in mind when you're designing and implementing a dual band wireless network, a network that supports both the 2.4 and the 5 gigahertz bands. Even though it's 2017, wherever I go, I still see lots and lots of single band Wi-Fi networks. That's the network that only supports the 2.4 gigahertz band. And so I think this is still a topic that we still need to cover. It's still something that we need to talk about and start getting those 5 gigahertz networks rolled out. I even see some vendors out there that are still selling single band hardware, which is surprising considering that we've had dual band hardware around for many, many years now. I kind of expected that by this time, I expected even by 2016, but that single band hardware would be pretty much non-existent, that we would see lots of things that supported the 5 gigahertz band, but it's still just not there yet. So let's go ahead and dive in. The first thing I want to talk about is one of the core things you have to understand about Wi-Fi. I talk about this concept whenever I talk about Wi-Fi. Whenever I give an entry-level topic, an entry-level discussion about Wi-Fi, I always start here because this is the cornerstone. This is the building block of Wi-Fi. You have to understand this and to kind of understand the rest of what's going on with this topic. So let's talk about what the half-duplex nature of Wi-Fi is. Now, I'm sure we're all familiar with Ethernet, and an Ethernet cable has multiple twisted pairs of copper inside the cable, and that affords us full duplex connectivity. With full duplex connectivity, we are able to send traffic in 2 directions at the same time. So when you've got an Ethernet cable, you can send traffic both up the cable and down the cable simultaneously, kind of like a 2-lane highway where you can send traffic east and west simultaneously. Wi-Fi, on the other hand, is half duplex, which means we can only send traffic in one direction at a time. We could, it's kind of like a 1-lane highway where we can only send traffic east or west, but not east and west simultaneously. It's also kind of like a human conversation. When you're having a conversation with a friend, if you both accidentally say something at the exact same time, you can't understand each other because you both just talked over each other. You can't understand them and they can't understand you. The same is true with Wi-Fi. If you've got a couple of Wi-Fi devices on the same channel, if they try to talk at the same time, they're just going to corrupt each other's transmissions and cancel each other out. Only one device can talk at a time. So what does a wireless conversation typically look like? Well, let's say that we have an access point here, and this access point needs to send some data to this client device. The access point is going to start out by doing what's called a clear channel assessment. It's going to listen to the channel to see if anything is talking on that channel. And if nothing's talking on the channel, then it's going to go ahead and take that opportunity to transmit data. So it'll transmit its data over to the laptop. Now, the next part of the process is the laptop is going to pull out the magnifying glass, and it's going to take a look at that data that it received to make sure that it understood it. And if it did, the laptop will go, yep, check, I understood the data, and it will reply with an acknowledgement, or we just call it an ACK for short in Wi-Fi. So it's this constant process of sending data and then the receiving device checking that data and then replying with an acknowledgement. But the key thing to keep in mind here is that only one of these devices can talk at a time. Now, here's something that is really important to understand for this specific webinar, is the concept of retries. Let's say that this access point transmits its data, but while it's transmitting that data, the data gets garbled up for some reason. Maybe it's because another device started talking on the same channel and interrupted that conversation. Maybe the laptop is just too far away to hear that transmission clearly. But for whatever reason, by the time that data gets to the laptop, it's just a big garbled up mess. So when the laptop looks at that with the magnifying glass, it's not going to understand that data, so it's not going to transmit that acknowledgement. The next thing that happens here is our access point starts to go, okay, well, I never heard an acknowledgement from the laptop, so it must not have received the data frame. So the access point is going to transmit the data again and again and again and again. It's going to keep retransmitting that data until finally the data makes it through to the laptop, and the laptop can understand it, and it can go, yep, check, I understood that data, and it can reply with an acknowledgement. This is a lot. This is a lot like my 2-year-old daughter. Actually, I've got 3 daughters. The youngest is 2, and she's in that stage of life right now where she has many, many questions. Those of you that have been around kids, you know what I'm talking about. If I'm reading a book or something like that, she'll come up to me and ask me a question. And if I don't give her some kind of answer, if I don't give her some kind of acknowledgement, if I don't acknowledge that she said something, she will ask the same question over and over and over and over and over, and until finally it makes it through to me, and then I can give her some kind of an answer or some kind of acknowledgement. So if you've ever had kids, or if you've ever been around kids, or maybe if you've just seen some kids from a distance, you know that kids are a lot like Wi-Fi in this way. And we're going to talk about retransmissions quite a bit more coming up next. So another thing we need to think about. We need to think about this on a broader scale. Instead of thinking about one access point and one client device, we really have to think about this on a whole channel. We have to think about it on a channel-wide standpoint. So if we, let's say that we've got a channel here, we've got an access point, we've got a few Android devices here, a few Android tablets and a few Android phones. Maybe they could be iPhones, maybe they could be Rokus, or pretty much any Wi-Fi enabled device out there. Any Wi-Fi enabled device is going to behave the same way in this instance. But if we've got a bunch of devices that are all on the same channel, and we've got a device that's transmitting, let's say this Android phone is transmitting to the access point. While that transmission is occurring, all the other devices on the channel have to be quiet and wait for their turn to talk. On any given channel at any given time, only one device can talk. Only one device can talk on a channel at a time, and that includes the neighbors as well. If there's a neighboring access point or a neighboring network with their own client devices, they all have to also take turns talking. We also have to factor in non-Wi-Fi interference as well. There's a lot of non-Wi-Fi devices out there, things like cordless phones, wireless video cameras, microwave ovens, baby monitors. All that stuff causes interference. It operates on the same frequencies as our Wi-Fi devices. And for example, a great example is the classic microwave oven. Microwave ovens cook food by bombarding it with lots of 2.4 gigahertz. Now, they have shielding built in to contain most of that, and so it's perfectly safe. But sometimes a little bit of that RF energy can leak out of the microwave oven. Maybe the door is bent slightly. Maybe the seal just isn't as good as it used to be. Maybe it's just an older microwave oven. But in that instance, when you throw a burrito in there and mash the 30-second button a few times, that microwave oven can start spewing out a little bit of interference onto our wireless channels. It basically just starts spewing out garbage that the Wi-Fi devices can't understand. But Wi-Fi devices know that only one device can talk at a time. So if they see energy on the channel, they will simply throw up their hands and back off and be quiet and wait for an opportunity to talk. Now, a microwave oven is just one example. There's lots and lots of things out there that can cause interference. Cordless phones, baby monitors, wireless security systems. There's all kinds of things out there. So watch out for those devices. They can absolutely bring a wireless network down. So when we're thinking about dual band wireless networks, we need to think about the differences between the two frequency bands that we can use. Those two frequency bands are 2.4 gigahertz and the 5 gigahertz band. There's some big differences between these two that I want to talk about really quick. The first one, and the most well-known one, is that 2.4 gigahertz has a greater range. It has a range of about 300 feet. Now that's going to vary quite a bit. It's going to vary based on your access points, the antennas that you're using, what the building is made of, how many people are in the building, and what client devices you have. But most vendors are going to advertise about a 300-foot range, and I think that's pretty fair. The 5 gigahertz band, on the other hand, has a much lower indoor range. It's only got a range of about 90 feet. Now, why is that? Why is it that 2.4 gigahertz and 5 gigahertz have such big differences in range? Well, it's because of the actual wavelength. 2.4 gigahertz is a lower frequency, so it has a longer wavelength. The wavelength is physically longer. It's actually almost 5 inches long. Whereas the 5 gigahertz band is a higher frequency, so the wavelengths are much closer together. In this case, if I remember correctly, they're about 2.3 inches long. I think 2.37 inches long per wavelength. check me on that. You might want to Google that before you start quoting that, because I may not remember that correctly. But the 5 gigahertz band, the 5 gigahertz wavelength is shorter, so it just doesn't do as good of a job of punching through stuff. It doesn't go through walls. It doesn't go through doors. It doesn't go through people and filing cabinets nearly as well as the 2.4 gigahertz band does. So we end up with a shorter range. And the funny thing about them, you put these outdoors in a field, 2.4 and 5 gigahertz have almost the exact same range. It's when you introduce obstacles that 5 gigahertz it sees a lower range. Now, the next thing to know about 2.4 gigahertz is that it is universally compatible. If you go out and buy a Wi-Fi device, you are guaranteed 2.4 gigahertz support. You're absolutely going to have 2.4 gigahertz support on a device, whereas in the 5 gigahertz band, we see limited compatibility. We see lots of devices out there that don't support the 5 gigahertz band. And this goes all the way back to 1999. In 1999, the IEEE released 2 new standards on the same piece of paper. One of them was called 802.11b, and it was a 2.4 gigahertz standard, whereas, well, an amendment, really. And then they also released 802.11a, which was a new amendment in the 5 gigahertz band. It opened up, is kind of a brand new piece of spectrum for 802.11 devices. So 802.11b had a maximum data rate of 11 megabits per second, but 802.11a had a much faster maximum data rate of 54 megabits per second. So it was significantly faster, but it didn't gain popularity. It didn't really catch on for a long, long time, mostly, I think, because of that range issue. 802.11b and 802.11a kind of had a format war going on. You remember VHS versus Betamax? Back in the day, my parents had a Betamax player, and they had about 5 tapes for it. Technically, Betamax was better, but the players were more expensive, and it wasn't an open format that anyone could use, and so ultimately, VHS tapes ended up winning out. The same thing happened here with Wi-Fi. 802.11b had greater range, and since we'd already been making 2.4 gigahertz radios for a couple of years, the chipsets were probably cheaper. So 802.11b ended up taking off in popularity, and 802.11a just never really caught on. And we're still feeling the results of that today. Today, if you go buy a Wi-Fi device, you're guaranteed 2.4 gigahertz support. But in the 5 gigahertz band, good luck. It really kind of depends on the device. For example, I just bought a budget Android phone just actually a couple of days ago. I picked up a blue R1 HD from Amazon, and this phone was unlocked, so it's not carrier locked, and it was $60. $60 will buy you a phone, and it's fine. I mean, the camera's kind of a potato, but beyond that, this has been a great phone. But one of the compromises of it being a budget smartphone is that I don't get 5 gigahertz support on this. I'm stuck in the 2.4 gigahertz band. Now, there are lots of devices out there that do support 5 gigahertz. Premium Android phones, pretty much every Apple device these days supports 5 gigahertz. I don't think the Apple Watch has a 5 gigahertz radio on board, but beyond that, every iPhone, all the way back to, I think the iPhone 5 was, all the way back to the iPhone 5 supports 5 gigahertz. Every MacBook Air, every MacBook Pro, they all support the 5 gigahertz band. But you'll still see a lot of those budget Android tablets, budget Windows laptops often have a single band, a 2.4 gigahertz only radio. A lot of streaming set-top boxes only support the 2.4 gigahertz band. One example is the first generation Google Chromecast is 2.4 gigahertz only, but then the second generation Google Chromecast supports 5 gigahertz now. So it's getting better and better, but there are still lots of devices out there that are stuck in the 2.4 gigahertz band. Now, 2.4 gigahertz, since it's kind of been the default band for so long now, is highly congested with Wi-Fi. There's tons of Wi-Fi in the 2.4 gigahertz band. Also, it is plagued with non-Wi-Fi interference. That nice little range advantage that 2.4 that the 2.4 gigahertz band gets makes it an ideal place for consumer electronics. Like we mentioned earlier, cordless phones, wireless video cameras, baby monitors are a really big one right now. Lots of baby monitors out there right now. Whenever I talk to technicians that work for internet service providers and I say baby monitors, they all groan, baby monitors, because that can really mess with Wi-Fi. Now, perhaps the biggest problem with the 2.4 gigahertz band, and this is really important, we're going to talk about this a lot in this webinar, is that in 2.4 gigahertz, there are only 3 channels to work with. Whereas in the 5 gigahertz band, we have 25, this says 24, it's supposed to be 25. I keep forgetting to get in there and change that. There are 25 channels for us to use. Now, earlier, we talked about how on any given channel at any given time, only one device can talk. We can only have one device talking on a channel at a time. And that means that each channel has a limited amount of capacity on the channel. There's only so much data that we can shove through a channel within a given time frame, since only one device can talk on a channel at a time. That means that the 5 gigahertz band gives us a lot more potential for a lot more capacity, because there's just a lot more frequency space available. Whereas in the 2.4 gigahertz band, there isn't a whole lot of frequency space available, and so we're really limited by how much data we can shove through the 2.4 gigahertz band. Now you might be thinking to yourself, okay, hang on a second, Joel. You're telling me that there's only 3 channels in the 2.4 gigahertz band. I've configured a few access points and routers in my day. Pretty sure there's more than 3 channels. Well, you're right. But here's the problem. The problem is how the channels are laid out. In the 2.4 gigahertz band, each channel, and this is true in 5 gigahertz as well, each channel is 20 megahertz wide. That's how wide a Wi-Fi channel is, whether it's in 2.4 or in 5 gigahertz. In 2.4, we've got our 20 megahertz wide channels here, but we've only got about 60 megahertz of space to work with in total. So you do some math, 60 divided by 20, you realize that there's only enough room for 3 channels in the 2.4 gigahertz band. So how is it that we have 11 channels in the 2.4 gigahertz band? Well, here's how. Each channel is marked by its center. So here's the center of channel 1, and it's still 20 megahertz wide. And then to find the center of channel 2, we're going to increment up 5 megahertz. So we're just going to go up 5 megahertz, and that puts us right at the center of channel 2. And when you visualize that, you realize that channel 1 and 2 overlap by about 75%. In the end, the only 3 channels that do not overlap are channels 1, 6, and 11. Those are the 3 non-overlapping channels. Okay, so that might bring you to another question. Why does it matter if channels overlap? Does it hurt anything? Yeah, it does. There's 3 different types of interference in Wi-Fi that we have to watch out for. 3 types of interference in 2.4 gigahertz specifically. The first is co-channel interference. Co-channel interference happens when we have a bunch of access points and client devices all sharing the same channel. Remember, we talked about this earlier. When we have a bunch of devices sharing a channel, they're all going to take turns talking. One of those devices is going to talk at a time. And as long as you don't get too many devices on the channel, that's actually going to work pretty well. That's actually going to work just fine. Think of it as kind of like a dinner table. If you, let's say that you have a couple friends over for dinner. And at our house, what we like to do is we always feed, if we have friends over for dinner, we feed the kids first, and then we send them off to the playroom to go play or something like that. And then the adults get to sit down and have a nice quiet dinner. So if we have some friends over, maybe my wife and I would have a couple of friends over. And when you've only got about 4 people at a dinner table, there's plenty of time for everyone to talk. You're all going to take turns talking politely, the conversation's going to flow, and you're all going to get an opportunity to participate in the conversation. But then think back to the last time that you had a family reunion or a big family get-together and you all crowded around one dinner table. When you're all crowded around one dinner table, maybe you have 15 or 20 people around one table and you're all having a conversation. If you're all engaged in the conversation, it can be really difficult to get a word in because there's lots of people that want to participate and there's just not enough time for everyone to get in and say what they want to say. The exact same thing happens with Wi-Fi. The more devices you add to a channel, the smaller and smaller everyone's opportunities to talk gets, and that is co-channel interference. The next type of interference that we have to watch out for is adjacent channel interference. Adjacent channel interference occurs when we have networks that are on partially overlapping channels. For example, we've got a network here on channel 5, a network here on channel 6, and a network here on channel 7. The problem is that each of those networks are on a partially overlapping channel. So instead of coordinating and taking turns talking politely, they're just going to yell and scream over each other, and it's going to be a very inefficient conversation. They're going to interrupt each other, which is going to cause retransmissions, which is going to cause them to have to talk again, which is going to cause more interruptions and more retransmissions until you just have a great big mess of noise. Adjacent channel interference is bad, 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 and we want to avoid it at all costs. And we can avoid it by sticking with the golden rule of Wi-Fi. The golden rule of Wi-Fi is that on any given channel at any given time, I'm sorry, that's the wrong rule, golden rule of Wi-Fi. The other golden rule of Wi-Fi is that we should always use channels 1, 6, and 11. If we only use 1, 6, and 11, then we'll ensure that we don't cause any adjacent channel interference. If everyone everywhere used 1, 6, and 11, Wi-Fi would work a lot better for everybody in 2.4 gigahertz. Now, the other thing that we have to watch out for is non-Wi-Fi interference. If you've got your wireless network here, and then you bring in a cordless phone, and that thing starts talking and spewing garbage all over a channel, then that's going to cause our Wi-Fi devices to back off. Remember that non-802.11 devices, that means non-Wi-Fi devices, also need time to talk, but they don't have the same politeness mechanisms built in. So we've got to watch out for that. Okay, so but what happens in the 5 gigahertz band? These are the types of interference that we see in the 2.4 gigahertz band, but what about 5 gigahertz? In the 5 gigahertz band, you'll notice that we still have co-channel interference, and we can still suffer from non-Wi-Fi interference, although it's quite a bit more rare. But where is adjacent channel interference? Well, remember, in the 5 gigahertz band, all the channels are laid out in such a way that they do not partially overlap with each other. If you use 20 megahertz wide channels across the board, you won't have any partial overlap. And so we don't suffer from adjacent channel interference in the 5 gigahertz band. We've removed that type of interference because the channel layout is better. Now, the next thing that we need to think about when we're thinking about co-channel interference and the half-duplex nature of Wi-Fi is how fast devices are talking. Let's say that we've got a phone that's relatively close to the access point, so it's able to maintain a nice fast data rate of 54 megabits per second. That's a nice fast 802.11g data rate. But then let's say that we've got another device that's on the very fringe of the coverage area. It's way out on the edge of the coverage area, so it's had to slow down to a slower data rate to make sure that the access point can hear it, and the access point is also talking back with a slow data rate. When we do that, when we've got this device out here that's talking more slowly, it's going to take longer to transmit the same amount of data. If these two devices need to transmit the same amount of data, the device that's closer to the access point is going to do it 54 times faster than the device that's all the way out on the edge of the coverage cell that's talking at a slower data rate. And this takes up more time. It takes up a lot more time on the channel because it has to slowly work its way through all of that data. Slower devices will limit airtime. They will take more time on the channel, and so they will consume the available amount of time on the channel. So we want to avoid this. We want to try to get devices to talk quickly. I like to think of the slow device as the slow kid in the back of the classroom. You know who I'm talking about? Have you ever encountered that guy? I'm sure you have. I think we all have. There's always somebody in a classroom. If you take a class somewhere, maybe it was in your high school, maybe a college class, or maybe something more recent where you've gone for training or something like that. There's always that guy in the back of the classroom that he raises his hand and everybody cringes because they know he's going to take forever to ask that question. He's going to say, teach? Yeah, I had a question about this particular topic. I was wondering isn't that uncomfortable? Didn't that just drive you crazy that you're sitting here in a webinar and you had to listen to that? We all know that guy, and that's exactly what this 1 megabit per second device is. These slow devices, these devices that have to fall back to slower data rates are the slow kid in the back of the classroom. And they eat up all of the time in the class, and those slow devices eat up all the time on our channel. So we want to avoid that. We want to make devices talk quickly. The other thing that we want to avoid is large coverage cells. We want to avoid having big coverage cells that encompass lots and lots of devices, because on any given channel at any given time, how many devices can talk? One device can talk on a channel at a time. So when we have a large coverage cell, we've got tons and tons and tons of devices that all have to take turns talking. And eventually we're going to run out of time on that channel. We're going to run out of opportunities to talk, and we want to avoid that. So how do we avoid that? With small coverage cells. If we can split up our big coverage cells into smaller ones, now we've got lots of little channels where all the devices on that little channel take turns talking, but instead of there being 30 devices on the same channel, in this example, now we've only got 3 or 4. Now that's a pretty extreme example to make sure it can fit on the slide, but we're going to make sure that we've got as few of devices on the channel as possible to ensure that each of those coverage cells have plenty of time to talk. Each one of these coverage cells is known as a contention domain, because all of the devices in that cell on that channel have to contend for airtime. And we want to keep our contention domains as small as possible. And that's going to lead us to a good, fast wireless network. The other thing that we want to do is deploy dual band access points, because that creates two contention domains in one coverage cell. We've got on our dual band access point, we've got both a 5 gigahertz radio and a 2.4 gigahertz radio. Now, the funny thing about a dual band access point is, from a client device's perspective, it's not one access point that offers both 2.4 and 5 gigahertz. It's really two separate access points that are contained in one box. Client devices view this as two separate access points. The great thing here is that we've got in the 5 gigahertz band, maybe we've got it configured to channel 36, and that's its own contention domain. And then in the 2.4 gigahertz band, we've got it configured to channel 1, and that's its own contention domain. So now we can split half of our devices over onto the 5 gigahertz band and the other half of our devices over into the 2.4 gigahertz band. And so now we have split our contention domain in half. So now we've got two contention domains once again. Now, there's a few things to keep in mind here. When you're rolling dual band access points, there's a couple of things to keep in mind about what name you should give it, what SSID you should give it. One thing that you can do is you can give both the 5 gigahertz radio and you can give the 2.4 gigahertz radio the same SSID. Now, that makes for a nice, clean user experience. For example, at home, both my 2.4 and 5 gigahertz radios on my access point at home are called Joel's Network. And so when somebody comes over, they'll pull out their phone and they'll see Joel's Network, and that's it. The problem with that is that your device, your client device, is going to make a decision about which of those radios to connect to. And most client devices do a pretty bad job of being smart about which one to connect to. 2.4 gigahertz is, as we discussed earlier, full of interference. It's full of adjacent channel interference. I've got dozens of other neighbors around, and I can hear all of their access points, and they're all causing some kind of interference with me. But every now and then, my client devices, even my dual band ones, will go ahead and connect to the 2.4 gigahertz band, ignoring that perfectly good green pasture of 5 gigahertz. And so that can be a problem. Now, Apple devices, I've noticed lately, Apple devices are really good about going for the 5 gigahertz band if it's available. My 2013 Nexus 7 that I have sitting here that we're going to use for a demo here in a bit, it's dual band. But here at the office at MetaGeek, we've also got the same SSID for both the 2.4 and the 5 gigahertz band. Even though it's got 5 gigahertz, it went for 2.4. So watch out for that. When you give them the same name, that can be a problem. Now, one way that you can combat that is with band steering. Enterprise grade APs typically have a function called band steering, where when a client device looks for networks, it'll actually intentionally avoid responding to the client device on the 2.4. So that way, the client device will go, well, I don't see any 2.4, so I'll go ahead and connect to this radio on the 5 gigahertz side. Now, after a few of those attempts, the AP will start responding on the 2.4 gigahertz band and allow that device to connect, and that's nice for single band devices. But that can cause some problems. That can cause your associations to be a little bit slower. So generally, I try to not turn on not turn on band steering, because it can introduce just a little bit more time that it takes for a device to get connected to a network, and it can cause some little bits of roaming delay and things like that. So your mileage may vary. Try it out with your vendor, test it in the lab, see how it works, but watch out for that. The other way that you can do this is you can give each network a unique name. You could call I could call one of them Joel's Network 2.4 and the other one Joel's Network 5. And that way I can force my device to connect to the one that I want it to connect to. I don't like doing that a whole lot because it makes for a pretty poor user experience. I have lots of friends in the Wi-Fi world, but believe it or not, I actually do have some friends that aren't in Wi-Fi. Crazy, huh? But when those friends come over, I don't want them to have to discern what Joel's Network 5 gigahertz means. They don't know. They just want to connect to some Wi-Fi and use the internet, right? So what I like to do is I like to do what I call socially engineered band steering, and that's where I'll actually give these names to kind of guide people to them. I'll call this one Joel's Network Fast, and then I'll just call the 2.4 gigahertz one just Joel's Network. So that way, when people pull out their phones and look at the list, if their device supports the 5 gigahertz, they'll see Joel's network fast, and they can connect to that one, and they'll get the better performance on the 5 gigahertz side. So that's a few different ways that you can handle the SSID issue when you're deploying dual band access points. And I like to call that last one socially engineered band steering. You heard it from me. Came from me. So the next thing we need to think about when we're designing a dual band wireless network is frequency reuse. Now, at home, I've only got one access point. I've got my good old Aerohive AP330 up on the ceiling. It's probably going to get swapped out for an Aruba here before too long, but or Ubiquiti, or who knows. I'm always switching around and trying out different APs. It's a lot of fun. I enjoy it. But at my house, I've only got one access point, so this isn't a problem. But as soon as you get into like a small, medium business setting, or an enterprise setting, or a factory setting, or a school setting, or anything like that, you're going to have more than one access point, right? When you need to support lots of devices and over a large coverage area, it's going to take multiple APs to cover all of this space. So in the 2.4 gigahertz band, you remember how we only have 3 channels to work with. We only have channels 1, 6, and 11 to work with. And you remember how only one device can talk on a channel at a time. So if we've got our original access point on channel 1, and we just start adding more access points on channel 1, we may be increasing our coverage, but we're not increasing our capacity, because those neighboring access points and all their clients are all going to have to take turns talking. So we need to perform frequency reuse to try to keep devices from having to take turns talking. So here's how we do it. When we're planning out all of our coverage cells, we're going to alternate between 1, 6, and 11, and we're going to try to keep our same channel access points as far away from each other as possible. Notice that the channel 1s are kind of far from each other, the channel 11s are kind of far from each other, the channel 6s are kind of far away from each other. We're going to try to keep these coverage cells from hearing each other if we can. And so we are going to reuse channels. We're going to go 1, 6, and 11, and then we're going to start reusing channels 1, 6, and 11, and 1, 6, and 11, and 1, 6, and 11, until finally we have populated our entire building and we have effectively reused our frequencies. Now, because 2.4 gigahertz has such a good range, it's very, very difficult to keep them from being able to hear each other. They're going to hear each other to some degree. Just because 2.4 gigahertz has good range and flies pretty far. One thing that I was really surprised about when I really started getting into Wi-Fi is that moment that I realized that 2.4 gigahertz having a quote-unquote range advantage isn't really a good thing. It's actually very difficult to deal with. I actually prefer 5 gigahertz because it doesn't go as far. It's very, very easy to make sure that that my coverage cells that are on the same channel can't hear each other. Speaking of 5 gigahertz, you're going to have to do frequency reuse in the 5 gigahertz band as well. We talked about earlier how there's 25 non-overlapping channels to work with in the 5 gigahertz band. That does make channel planning a lot easier because there's just way more channels to cycle through, and it also doesn't fly as far. So dealing with co-channel interference and making sure that you've properly reused your channels is a lot easier. Just make sure that you're keeping your same channel coverage cells as far away from each other as possible throughout the design process. So let's talk about range for a minute. In this example, I've got a site, this is a site survey tool specifically this is Ekahau, which is a product that we don't make it, but we're good friends with the team over at Ekahau, and they're resold. They're resold here by Microcom. So be sure to ask them about Ekahau. Another great tool out there that I believe Microcom also resells is Tamograph, another great one, and ask them about their options. They've got lots of great tools that are very similar to this one. Now in this example, what we've done here is we've taken a site survey tool, and we have uploaded a floor plan into this tool, and then we've gone in and we've drawn in our wall types. We've said, okay, this is a brick wall, this is a brick wall, this is a brick wall, this is drywall, and then we can drop in a virtual access point, and the software will calculate out what the coverage area looks like. And so that's going to give us a good idea of how we need to design our wireless network. We can get in here and we can design our network before we even install any access points. And it's going to simulate range for us. Now, notice here that as we move away from the access point, our data rates go down. We start at 150 megabits per second, very, very close to the access point. And as we move around to the edges, we start seeing lower and lower data rates all the way down to between 1 and 11 megabits per second. So we see good indoor range, and it covers a big area, and that's typically good, right? That's typically a good thing that we have lots of range, right? Well, let's go take a look at the 5 gigahertz band and see how it compares. In the 5 gigahertz band, whoops, that's supposed to say 5 gigahertz there. In the 5 gigahertz band, we can see that that we've got a smaller coverage area, right? And that's typically bad, right? So we've kind of got this problem where in the 2.4 gigahertz band, it flies pretty far, so we get lots of coverage. But when you look at our coverage map, when you look at what's going on, you can see that we've got these large swaths of areas that are going to have low data rates. All these areas around the edges are going to be full of slow talking devices. In addition, we've also got a big coverage area here. We've got half of this building covered with one access point. So we're going to have a lot of trouble with a lot of devices connected to the same access point and on the same channel. Whereas in the 5 gigahertz band, we've got range issues. If this was the same dual band access point, the 5 gigahertz band doesn't have as good of coverage, and so a lot of people aren't even going to be able to use that. So how do we deal with this problem? Well, here's what we do, and this is a bit of an exaggerated example, but it drives the point across. Instead of just doing one dual band access point that tries to cover half the building, we're going to do lots of access points, lots of dual band access points throughout the building. So we've turned down the transmit power on all these to make them cover very, very small areas. They're all covering very, very small pieces of the building. So we've split up our contention domains. We are only using channels 1, 6, and 11 here. So we have eliminated adjacent channel interference. We've minimized co-channel interference by keeping our same channel access points as far away from each other as possible. Because we're providing both 2.4 and 5 gigahertz connectivity, we have doubled our potential wireless bandwidth. We've also provided B, G, and N compatibility for those 2.4 gigahertz only devices. My little cheapo blue R1 HD is going to walk into this building. It's going to work fine. It's not going to be super fast, but it will work. I will still have access to Wi-Fi. Whereas the faster 5 gigahertz devices that support 802.11a and 802.11ac are going to have a much faster network to connect to. We're going to see lower retry rates because we have eliminated adjacent channel interference, and we are going to overall have a lower impact from interference from other devices. So that is an example of how a good, well-designed network is going to provide us with all of these advantages in both the 2.4 and the 5 gigahertz bands. Okay, so what I want to do now is I'd like to kind of take a look at the differences between 2.4 and 5 gigahertz. And so what I'm going to do is I'm going to take IPA. This is our product. This is a product here offered by this is a product by MetaGeek and available through Microcom. I love this tool. It's a lot of fun, and I'm going to show you why. What I've got here is I've got 2 tablets. I've got my trusty old 2012 Nexus 7 here. Now this is a single band device. Then I've got my other trusty Nexus 7. This one is a 2013 Nexus 7, so it's a year newer. It's still getting kind of old at this point, but I will give up my Nexus 7 when you pry it out of my cold, dead fingers, because I love this tablet. It's just a great little tablet. Now it's got 5 gigahertz, so what we're going to do is we're going to perform a packet capture in the 2.4 gigahertz band on channel 6, which is what my older Nexus 7 is connected to. So I'll go ahead and start that packet capture, and then we're going to run just a speed test. Speedtest.net, your classic internet speed test. A better way to do this would be with an iPerf server. That would probably give us a better idea, but I don't have one set up right now, so this is going to work just fine. So I'm going to go ahead and begin the test now, and so now IPA is capturing this entire conversation between my 2012 Nexus 7 and the access point. Hey, we're seeing pretty good data rate actually. We're seeing about 21 megabits per second right now. So we finished our download test. Now we're doing our upload test. We're hitting about 10 megabits per second. Overall, this is looking like a pretty good test. This is going pretty well, especially in the 2.4 gigahertz band. Okay, so we've ended our packet capture. So let's go ahead and stop it. And then let's go ahead and head over to, let's go ahead and take a look at this packet capture and see what happened. IPA is going to crunch all the numbers and figure out what happened during the packet capture. Okay, so if we look at the airtime chart here, we can see that this network called MetaGeek took up the most time on the channel. If we move one more layer out now, we can see that there's one access point here that's part of the MetaGeek network. That's good. We don't want multiple MetaGeek access points on the same channel because then they'd have to take turns talking, and that's bad. And then we move one more layer out, and we can see this Asus device. Now, the Nexus 7 was manufactured by Asus, and so this is probably our Nexus 7. Now, the thing that I want to do here is I want to look at the retry rate. That's the specific thing that I'm after here is what is the retry rate? Amazingly, the retry rate here was only 8%. That's a nice data rate. Anything more than about 20 or 30, I start to get concerned. So we're really, really well within parameters here. This is looking pretty good. I'm also curious about what data rates we used. It looks like 59% of the time we use 24 megabits per second. And then about 35% of the time, we use 65 megabits per second. So we use nice, fast data rates. Now notice that we never really dropped down below 24 megabits per second. And there's a very specific reason for that. The reason why we never dropped down below 24 megabits per second is because we disabled legacy data rates. We turned off data rates 1, 2, 5.5, and 11 megabits per second. And we also turned off 6, 9, and 12, I think, as well. So we have ensured that you can't use those slower data rates, and that has forced our device to talk faster. So that's another design tip that you can take is you can turn off legacy rates. Just keep in mind that decreases the range of your access points a little bit. The packets just won't fly quite as far. Okay, so 8% retry rate. Let's go back to our packet capture tool here. And let's go ahead and check this with the 2013 Nexus 7. Now, one little caveat that I'm having here is I am actually not sure which channel my 2013 Nexus 7 is connected to. So I'm going to find out really quick here. Let me figure out which channel it's on. There's a couple of ways that you could do this. I'm using a tool that's on the Android device specifically to find out. But one thing that you could do is you could run a throughput test and look at it with a spectrum analyzer and see where all the activity shows up if you looked at it with a Y-Spy or a copy of Channelizer. Okay, so it looks like I'm on channel 48. So let's switch over to the 5 gigahertz band, and we'll capture on 48. So here we go. And we're not going to save our previous capture because I'm not worried about it. So now that we've got our packet capture running, I'm going to go ahead and run the exact same app. I'm going to run my, my speed test. And it's looking for a server. And then we'll begin our test. Okay, so now we are working on our download test. We're pulling down 40 megabits per second. So we had 20 with the 2.4 gigahertz only tablet. We're pulling down a solid 42, 43, almost 44 megabits per second. And I happen to know that our fiber line here is only 50 megabits per second. So we're realizing most of the available throughput. And we're seeing an upload of about 12 megabits per second. So nice. That's looking like a good solid test. Okay, notice that was done a lot faster. We didn't have to wait as long for the test to finish because it was quicker. So now let's go ahead and check out this packet capture and let's see what happened. Oh, the suspense. All right. Should be getting some data about now-ish. There we go. Okay, so we can see that really MetaGeek was pretty much the only thing that talked on this channel, right? We pretty much had the channel to ourselves. Now, we did have a little bit that we couldn't figure out where it came from, and we did have a little bit from one of my access points over in the lab called MetaGeek Console, but mostly it was from MetaGeek. Of course, only one access point and one client device that did most of the talking, and check out the retry rate. The retry rate was only 4%. That is excellent. Very, very good. Now, notice the data rates aren't really different. We had a lot of 24 megabits per second, and we had a lot of 65 megabits per second. Same data rates, but less retries means that we saw twice the speed on our actual throughput with our speed testing application. So we saw much, much better performance in the 5 gigahertz band just because of the difference in retries. Okay, that wraps up what I had to show you today. So I think I'd like to go ahead and open up the floor for questions and hand it back to Julie. Julie?
Thank you very much, Joel, and thank you for that wonderful presentation. And yes, we definitely have some questions. Let's see, let me get started here with our first one. Let's see, when you said you see a lot of single band networks, One of our salespersons are asking, is there a list we can call for you? Perhaps we could sell this dual band. You know what I mean?
That's a great question. You know what you guys can start doing is get yourself a Wi-Fi scanner on your phone. Get yourself an Android phone. Get yourself a $60 Blue R1 HD. Actually, it doesn't support 5 gigahertz, so you need something that's dual band. But everywhere that I go, I look at a Wi-Fi scanner all the time. I mean, being a Wi-Fi guy, it's what I do. I'm always checking. Like, we go to Walmart, and I'm like, do they have 5 gigahertz Wi-Fi? I'm always curious to see how their network is and whether it's deployed well or not. I do that everywhere I go. So start carrying around a Wi-Fi scanner and just check it out. That's what I do. And yes, I see lots and lots. In fact, about a year ago, I went down to the local library, and I was really disappointed to see that they had actually ripped out their dual band gear and replaced it with some budget single band gear. Instead of redesigning the network and just fixing what they had, they replaced it with single band gear. And I was like, oh, that hurts. So yeah, start walking around with a Wi-Fi scanner, and you'll be amazed. It's all over the place.
Thank you for that, Joel. Next question. Are there tri-band or quad-band networks?
Ooh, that is a good question. So you will see if you go down to your local Buy More store and look at the that's your local electronics store, and if you look on the shelf there, you will notice that there are lots of Soho, small office, home office gear that are claiming to be tri-band. What they really mean by that, they're not technically wrong, but what they really mean by that is that it is a tri-radio device. Usually they've got one 2.4 gigahertz radio and then two 5 gigahertz radios. For home use, I think it's way overkill. I mean, I don't know when you'd ever need that. We are starting to see some tri-radio devices in the enterprise world where they're actually shipping access points that have two 5 gigahertz radios. So that gives us a total of 3 contention domains. The nice thing about that is that you can stick all of your legacy devices on the 2.4, and then you could stick all of your newer devices on the 5 gigahertz, and then you could stick all of your voice over IP phones or something specific on the other 5 gigahertz access point. So that's a great idea, and I think there's some potential there, but we only have 25 channels to work with. Spectrum is very, very limited, and in very dense environments like hospitals and stadiums, the tri-radio thing might not work. The third place that you'll see the tri-radio devices is there's a lot of consumer mesh devices out there now. There's Eero, there's Luma, there's Netgear's Orbi, there's Google Wi-Fi. It just goes on and on and on. 2016 and 2017 have been the years of home mesh Wi-Fi. They are also starting to put 3 radios in their devices now, which I think is actually a really good idea because they can dedicate the third radio to backhaul between those mesh nodes, and so I think that works pretty well.
Thank you very much for that, Joel. I got a comment here that someone says that is the analogy you gave in regards to kids being like Wi-Fi. That's like the best analogy ever.
I use that analogy every time I teach a webinar or teach a class.
Yeah, with those of us who have kids and even those of us who don't, we get it.
Yep, that's right.
Next question for you. When you discuss the range that the range is 300 feet in each direction of where the unit is stationed, is that in each direction?
Yes, so when I say 300 feet, I'm kind of operating on the assumption that we're using omnidirectional antennas. That's antennas that go in all directions, basically. They're not a perfect sphere. They're more like a donut, but more or less they go in all directions. So yeah, when I say 300 feet, I'm mostly talking about an omnidirectional antenna. Now, you can take a directional antenna, a very, very focused antenna. Think of it as kind of like a flashlight instead of a lantern, or maybe even a laser pointer, and you can get Wi-Fi to go very, very far. I know of some guys, I want to say it was 6 or 7 years ago, something like that, down in Nevada. They achieved a 120-mile unamplified Wi-Fi link by using highly directional antennas, 120 miles. So it all depends on how much you focus it down. So yeah, 300 feet, that's assuming that you're using omnidirectional antennas.
Thank you, Joel. It looks like we're going to wrap it up with this one last question. Why can't devices come locked to specific channels in 2.4 to ensure that those 3 channels are the only options?
That is a wonderful question. And every time that I'm in front of a vendor, whether it be a Soho vendor or an enterprise vendor or a small, medium business vendor, I always ask them, please, 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 please make it so that you can only use channels 1, 6, and 11. Now, there are some corner cases where you might want to use the other channels. And so, maybe you just stick a checkbox in there that says, show non-standard channels, and then there'd be a warning that says, warning, this might be a bad idea or something like that. Great question. Whenever I get in front of vendors, I ask that every single time. So we'll keep fighting for it, and maybe someday we'll get there.
Sounds good. Thank you very much, Joel, for answering those questions. And thanks to everyone for attending today. And if anyone has any other questions, please feel free to contact your sales rep or email us at sales@microcomtech.com. And if you wish to view any products mentioned or shown today, please visit us at www.microcom.us. And remember, this webinar presentation has been recorded, and it will be uploaded to our YouTube channel, so you can reference it again and view it all again. Thank you very much, everybody. Joel, wonderful presentation. Everybody have a fantastic day.